So now let's continue into the solidification for heterogeneous nucleation. Heterogeneous, which means it's happening at not homogeneous, at specific locations. Let's think of what would be the rate and what would be the so-called energy barrier. And also we'll talk about the growth of pure solid from liquid. Okay? So heterogeneous nucleation, the actual nucleation quite often, the formation of the initial cluster, solid cluster, and from there the solid will grow. Like in the video, they put a seed, the second part of that experiment. They put a solid ice crystal in within that. They don't need to shake. They just put that the solid piece of ice in there. That acts as a specific location. And from there, nucleation starts to happen quickly. That's what we call heterogeneous nucleation. It happens involve sometimes the wall, container wall, insoluble oxide if we are dealing with metals. We are casting liquid metals into a mold, and the liquid metal is metal, but occasionally you would have so-called insoluble oxide, aluminum oxide within aluminum, silicon dioxide within liquid silicon, something like that. Those would act as our nucleation sites, specific location for the so-called heterogeneous at a specific location to happen, okay, which become the so-called substrate for heterogeneous nucleation. And if we simplify, we want to simplify it to understand. If we assume gamma interfacial energy between M for the mold, which is quite often a type of heterogeneous site mold, and the liquid is isotropic, which means you don't depend on orientation of the other one. If we assume our substrate or mold is what? Flat, horizontally flat. Local radius of curvature is 0. Curvature is 0. The radius curvature is infinity. We would have something like this, right? The flat solid existing is our mold of substrate of foreign material, solid material, right? That's hetero. It's happening there, not uniformly within the liquid. Above it is our uniform liquid, and in between, that's our solid nucleus, or solid cluster that would form. And for simplicity, we assume to be a so-called sphere cap. For simplicity, of course, it may not take that shape, but for simplicity, let's treat it as a sphere cap. And the radius curvature of that sphere cap would be defined as R. Okay? So heterogeneous nucleation is happening at the mold of substrate between the liquid. Okay? It's occurring over there. And we assume it's isotropic, doesn't depend on orientation. It's flat to simplify the geometry. Okay, and then if we think there will be several so-called interfacial energy term or force term. One would be between mold and liquid. Between mold and liquid, that interfacial energy is trying to shrink what? Between mold and the liquid, that interfacial energy is trying to shrink the interfacial area between what? Mold and liquid. So if I have a solid, that red one is trying to make this nucleus even larger because it's trying to shrink the interfacial area between what? Mold and the liquid, shrink it. On the other hand, between SL, between what? Solid and the liquid, it's trying to pull the other way because it's trying to shrink the area between what? Solid and the liquid. The other one is SM, S for solid, M for mode of your substrate. Between your solid and the mode is also trying to shrink the other way. Make sense? It's also trying to contract. So we would have a local force. And let's say under a local steady state or equilibrium condition. Do you see mathematically? We would have this relationship, right? The mode, liquid, going towards right would be solid mode going towards left plus the projection of what? Solid liquid cosine term projected onto horizontal. This is okay. Assume my cluster solid reach kind of equilibrium. Make sense? That's our relationship. Okay? And then the so-called free energy change. We are considering nucleation. Free energy change in heterogeneous nucleation. Initially, it's what? All before the formation of this solid nucleus, semi-sphere cap nucleus. Initially, it's just the liquid and what? Mode. And now we have liquid mode. Between it, we have a solid sphere cap cluster or nucleus, right? So this free energy change, I'm going to write it as this. Delta G HET for heterogeneous nucleation. The free energy change would be these terms. The first term is what? Delta GV, the volume free energy change times what? Vs. What is Vs? Solid, which is our sphere cap volume for that. And this term is our kind of driving force. But then in this process, we are adding, we have two plus signs. We are adding two interfaces. What are those two interfaces? One interface is between what and what? Look at where I'm pointing. I'm adding an interface between S for solid, L for liquid, right? Before that, there's no solid. Now I'm adding a solid liquid interface, which is from here along the sphere cap surface to here, right? This is our ASL times gamma SL. That's our added one interface. We are also adding what? We are also add an interface between what and what? Solid and mode, because between here and here, initially it was what? Between here and here, initially before nucleation, between here and here, it was liquid and solid. Now we are changing it from liquid solid to solid and mode. Between solid and mode or substrate. This is our area from here to here, right? Area times interfacial energy. But then we also eliminate part of an interface. Between what and what? Look at this gamma term. Between liquid and the mode. Between here and here, we eliminate the interfacial energy between liquid and the mode. But what's the area? It's the same area as solid and mode. Make sense? So this is our free energy change term, the net. We are having a volume free energy term. We are adding two interfaces. At the same time, we also eliminate one interface. Make sense? And then we said, for simplicity, we assume what shape? Sphere cap shape. Okay, sphere cap geometry. And mathematically, we don't go into the detail. That's what you learned in high school. ASM, what does that mean? Between the area between solid and the mode, between solid and the mode, is pi r squared. If this is r, what does r mean? Sphere cap radius. Okay. And what is, if this is our angle theta, do you see this is also theta? If this is angle theta between the nucleus and the mode, do you see this is also theta? Because this angle and this angle adds up to theta, and this angle adds up to 90. This guy and this guy also adds up to 90. So this is theta, this guy must be theta. If this is our radius, do you see from here to here is r times sine theta? Make sense? From here to here is r times sine theta. So pi r sine theta squared, that's the circle area from here to here. Make sense? That's our between S for solid and for mode, from here to here. Okay? ASL is the area from here all the way to here. The sphere cap area is 2 pi r squared 1 minus cosine theta. Let me ask you this. If theta is 90 degrees, what shape is this sphere cap? If theta, this angle is 90 degrees, that is half of what? Half a sphere, right? When theta is 90 degrees, cosine theta is what? When theta is 90 degrees, cosine theta is 0. Okay, 1 minus 0, you got 1. 2 pi r squared, that's also exactly half of a sphere surface area, right? That is, makes sense, right? The area from here to here. And on the other hand, when theta is 0, one minus 1, that's 0, right? We also have 0 area. Make sense? Okay. So that's our relationship. And the V, that's the 2 pi 4 over 3 pi r to the power 3 times this term. But again, when theta is 90 degrees, this term becomes 0, right? 1 minus 0, 1. And then theta is 90 degrees. This is 2 plus 1 equals, 2 plus 0. And 2 over 4, that gives us half of sphere volume. That's theta is 90. That's exactly half of sphere. Make sense? That's just we check a few numbers to make sure, okay, this kind of makes sense. We don't go into the mathematical detail. That's your high school geometry. Okay? So this is what we have. VS term, ASL. When we plug all these numbers to L, to this, right? We're going to plug all these to the data G, heterogeneous, and then we are going to have this. After we simplify the mathematics, we are going to have the data G heterogeneous would be within the square bracket times a S theta. S theta means it's a function of what? Theta, also called a writing angle. Kind of writing angle, right? And the writing angle is just the proportion of the sphere cap to the whole sphere volume. Make sense? It will be within the bracket, square bracket times this I theta. And this I theta only depends on what? I theta term only depends on theta times within the square bracket. But if you stare at it a little bit, within the bracket, that is just our homogeneous nucleation energy. Make sense? Volume times delta GV, area times gamma, right? So that's what we have. Heterogeneous is square bracket times S theta, and we said S theta only depends on theta. And remember, within the bracket, square bracket, that whole thing is just our homogeneous nucleation energy, the free energy change for the homogeneous case. As a result, the heterogeneous free energy change would be homogeneous energy change times S theta. Okay? And then, of course, S theta, we said it's the ratio between the sphere cap to the whole sphere. And it's always smaller than 1. It's always smaller than 1. As a result, we are going to plot, if I'm going to plot delta G versus what? R. And the red curve is for homogeneous. The highest point is for the so-called critical nucleation energy or nucleation barrier. And this blue one is for heterogeneous, and it's related by this S theta, which only depends on theta. It's just the homogeneous times S theta term. Okay? And because this S theta term does not depend on what? Radius. Only depends on S theta, only depends on what? Theta. And if we take so-called first derivative, we would end up between here and here, we would end up the same nucleus size. The heterogeneous and the homogeneous, they would have exactly the same so-called R star, which means the highest point would occur at exactly the same size, R star. Okay, this is what we have. Heterogeneous versus, okay, homogeneous. For the same liquid, metal, same ice or whatever, whether it happens homogeneously, which means it happens anywhere within the liquid, or heterogeneous, happening at a specific wall, they would have the same what? Critical radius. Critical radius. Critical radius is kind of the, we are assuming they're part of a sphere, the so-called radius of curvature. They would have the same value. Okay, but sorry, the homogeneous one would have much lower what? For any cluster, they would have much lower activation energy or barrier, right? It's much easier for the system to overcome this than for the system to overcome the red one, the homogeneous one. Okay? Question?